The views expressed on Science for the People are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
So lithium-ion batteries, that's more for your high-power applications in the shorter term, whereas a redox flow battery system will operate for a long time because it has a massive capacity.
This week on Science for the People, we take a deep dive into modern batteries, how they work now and how they might work in the future. Later on, we'll speak with Kathryn Toghill, an electrochemist from Lancaster University, about redox flow batteries and how they could help make our power grids more sustainable. But first, let's learn more about the most commonly used batteries today, how they work, and how they could work better. Welcome to Science for the People. I'm Rochelle Saunders. With me is Gerbrand Ceder. He's the Chancellor's Professor of Materials Science and Engineering at UC Berkeley and has served on MIT's Energy Council and on several DOA committees, including the work group preparing the Basic Needs for Electrical Storage report. He's also on the Safety Advisory Board for Samsung and has advised the government's Office of Science and Technology Policy on the role of computation in materials development. Gerd, welcome to Science for the People.
Thank you.
So before we start talking about the future of batteries, I want to back up a little bit for anybody who maybe doesn't remember high school science. Can we talk a little bit about how the batteries we currently have today work?
Sure. So we normally distinguish rechargeable and non-rechargeable batteries. Actually, in the jargon of the field, they are called primary and secondary. The primary ones being the ones you can that are disposable, like your classic alkaline battery, and secondary being rechargeable batteries. So we mostly work on rechargeable batteries, but in general, a battery is a device where you convert chemically stored energy to electrical energy, and the way that's done is in a sort of very clever way. Usually, you have two electrodes and the material on one wants to violently react with the material on the other one, but it can only do that internally by moving the ionic form of the material to the other side. And so as the ion goes from one electron to the other side, it sort of pushes electrons through the external circuit, and that's how you get electricity out of a battery. So it's really a clever device to convert chemical to electrical energy.
So what is the difference between how a rechargeable battery works and a non-rechargeable battery?
Yes. Well, so it really just, there's not a big difference. It really is that in a non-rechargeable battery, that reaction that occurs inside the battery is extremely hard to revert. It's not theoretically impossible, it's just practically very hard to do. And a rechargeable battery is designed so that you only do reactions that can be reverted. So, as in, say, discharge, an ion flows from the anode to the cathode. In charge, you can push it back. And that's, for example, the case in lithium-ion batteries, and we can talk more in detail about that. Whereas in primary batteries, you just can't do that.
So is that mostly due to the materials they're made of?
Yes, it's due to the choice of chemistries that this is made of. For example, in let's say, your typical primary, alkaline battery, you have a zinc anode and a manganese dioxide cathode. And what the zinc anode does, it reacts with water because the electrolyte is aqueous. It reacts with water, makes zinc oxide or hydroxide. That releases a proton. The proton kind of moves through the electrolyte to the other electrode, inserts in the manganese dioxide, and reduces the manganese dioxide. Parts of that reaction would be reversible, and you can make alkaline batteries that are sort of like poorly reversible. That's, by the way, why you can buy these sort of rechargeable alkaline batteries, but they only do like 20 or 50 cycles. But the reaction on the anode, which was zinc to zinc oxide or hydroxide, is very difficult to revert. Whereas in rechargeable chemistries, like, say, lithium-ion, we only work with electrode reactions that are very reversible. And that's why you can then do hundreds or thousands of cycles.
Interesting. So I'm curious because I've never actually seen the inner workings of a battery. So if we, say, took apart my phone and pulled the battery out of it, what would I actually see if I took the battery apart? Not that I advise we do this, but
No.
What would happen if I did? Like, what would I see?
Cool question. So what you actually find is what's called, it's actually called a jelly roll. So what you should imagine is imagine that you put a bunch of sheets of paper together, and maybe you put some aluminum foil with it and plastic foil, and you sort of cut a really long strip of that multi-layer, and then you kind of roll it up. That's actually how the battery would physically look like. And it's actually, you can sort of imagine, right? You roll it up, and it actually looks like a jelly roll. And sometimes that jelly roll is kind of squished flat. Sometimes it's just cylindrical. And what each of these layers does is each of these layers is an active component in the battery. For example, let's take a lithium-ion battery. You would start with a metallic foil, which say collects the current on the anode, and typically that's aluminum or copper. And then you would have an electrode layer, which in the case of a lithium-ion would be a layer that contains a lot of graphitic carbon, just like in old-style pencils and stuff, with a polymer that binds it together. And then there would be a plastic layer to protect that from the next layer. That's called the separator. And then you would make the cathode layer, which is just like the anode layer, but now with a specific oxide material that can hold lithium ions. And then you slap the top current collector, and you have this sort of multi-layer sandwich, and you would kind of cut it in like narrow strips, and then you would roll it up, add context to it, put it in a packaging, whether it's a hard shell or a pouch, and that's how your battery would look like.
Okay, so sometimes, especially with the non-rechargeable batteries that I might buy, if they've been sitting around too long, sometimes they get like a kind of gross buildup on the outside. I feel like they're leaking something. What is that?
Yeah, so in alkaline batteries, that's actually potassium hydroxide. So the electrolyte in a primary battery, an alkaline battery, is extremely corrosive. Actually, the word alkaline refers to the alkalinity of the electrolyte. So in technical terms, that's actually what's called the pH. And you may have from your high school days remembered pH is something that sets like the acidity of a solution. Water is neutral, is what's called pH 7. If you make like really, really strong acids, they would be like pH 1. And high alkalinity is the opposite. It's like pH 13 or 14. And both extremes of the scale, high acidity and high alkalinity, are extremely corrosive. And so what happens if this electrolyte is contained in that can, right? Imagine your alkaline battery. It's it's all packaged in a can. And over time, it can corrode the can. And as the can starts to leak, the electrolyte dissolves out and the water evaporates, and it leaves potassium hydroxide as a salt behind. And that's the kind of whitish powder that you see.
Mm-hmm. Okay, so that is actually something that's coming out of the battery.
Yes.
Okay. So with lithium-ion batteries, in particular, I am thinking about my current phone's lithium-ion battery because I've been having some problems with it. It's not holding a charge for as long as it used to. So obviously there is some kind of problem with the battery, I guess. Is that just like a defect with my one battery, or is that something that's kind of inherent in a lot of lithium-ion batteries?
So it's not a defect. It's I hate to say it's by design. It's not quite by design, but it's assumed that you can tolerate it. So what happens? So first of all, lithium ions are very high energy devices. To put it in perspective, your alkaline battery is like 1.5 volt, right? Mm-hmm. A single cell lithium ion, which the sort of equivalent is about 4 volt. And 4 volt in chemical terms is an enormous amount of energy. It's an enormous amount of driving force, actually, for energy. And so what happens in lithium ion batteries when you charge them to fairly high voltage is that the electrode materials will react with the electrolyte. So remember, right, these films all sit in some kind of electrolyte. They react, and that causes reaction layers which slow down the charge and discharge. You could think of it as, the technical word is polarization. So what actually happens is that, your charger has some algorithm that decides to cut off the voltage of the charge when it reaches a certain number, say 4.4 volt, right? Mm-hmm. So your phone will charge and it pushes up the voltage more and more and more. And when it reaches a certain voltage, it cuts it off. When the battery gets older, what actually really happens is that at that voltage, it doesn't really take that much charge anymore because it's what's called polarized. And so there's nothing inherently wrong with the materials in your phone. It's just that they're just not as nimble anymore in taking up charge. But the reason why that's a real problem with your phone is that phone batteries are designed for maximum energy content, because we all like really long talk time, and the industry kind of realizes that you're going to replace your phone every 18 months or 2 years anyway. So they push the charge and therefore the energy cutoff so high that there will be some capacity fades. But in return of that, you get higher energy content in the beginning.
Oh, interesting. So it's a known trade-off.
It's a known trade-off, yeah. We could give you batteries that last 10 years, but you would get somewhat lower energy content. And by the way, that's what we do for other applications, right? You know, when you're going to buy your Tesla or other electric car, you don't want that kind of capacity fade, right? Because you want it to last more than 18 months or 2 years. And so there, they will set the trade-off in a different place. The energy content will be a little lower, but you will have much better lifetime.
Interesting. I didn't realize I just assumed that was something inherent in lithium-ion batteries, that I didn't realize there was an active trade-off happening. That's interesting. It's
really cool because you can actually, you know, like for grid applications, right? If you now put large industrial lithium-ion batteries in the grid, you can actually make batteries that cycle for 10 years. No problem.
Wow.
Yeah.
Huh. So other troubles that people have with batteries, one that was in the news not so long ago and that you are well acquainted with, Samsung had some issues with exploding batteries. So first of all, can you talk a little bit about how a battery can explode?
Right. So part of it has to do with the fact that, you know, you're asking for a very high energy content in a small package, right? So and the whole success of batteries is that they have found the mechanism by which you can release that gradually. To put in, so the way I started this conversation is that I said, you know, you have two chemicals that want to react heavily together. That's how you can store the energy. It's called the anode and the cathode material. And if they actually come in contact with each other, they do react violently. And to put it in perspective, they are in an actual battery, they're only separated by about 10, 20 micron. And that's that film that goes in between when I talked about the construction of a battery. And to put it in perspective, 20 micron, that's like less than the width of a human hair, right? Human hair is about 100 micron. Mm-hmm. So that's how close these things sit together. And remember, we don't want to let them touch each other, because if they touch each other, we're in trouble. So you get this large amount of energy that you want to only release in a gradual way. So what can go wrong? So what can go wrong, for example, is if this separator material, which is this plastic foil that's 10 to 20 micron, if that's damaged, for example, if that's damaged, then the two electrodes may push because of external pressure, for example. They may come in contact with each other. And now what happens is that your battery essentially discharges all its energy internally, right? Yeah, when you use your phone, you're sort of discharging the battery and using up the energy in your phone, right? Or I could, you know, use a light bulb or drive a car. Mm-hmm. If you have this internal contact between the electrodes, an internal short, then all the energy gets released internally. And so imagine, right? So you have this enormous current suddenly going inside the battery instead of outside the battery. And that heats up the battery. And as the battery heats up, unfortunately, faster and faster. So you get into this self-accelerating cycle, and that ends in explosion. And by the way, this whole process that I described can happen in just a few seconds.
Wow. So it
took me a long time to explain, but it once you have a short, the battery heats up really fast, releases more energy, and it vents gases, now and the thing explodes.
Wow. So it is definitely very important that you not try to damage your own batteries intentionally. It sounds kind of dangerous.
Correct. That's you definitely never want to drive a nail through them, especially when they're charged. You know, when they're discharged, it's less of a problem because they don't contain much energy. But when they're charged, you definitely do not want to cause any internal short. And actually, a typical safety test in the industry is what they call the nail penetration test. There is a test that all batteries have to pass. That is, a nail gets driven through them and they cannot explode.
Wow. So does the potential explosive nature of batteries, if they're damaged, cause problems with something like an electric car, since a car is something that, let's face it, gets into car accidents, and some of those car accidents smush up cars pretty badly?
So I think the first thing to say is that the incident rate with lithium-ion batteries is still very small. So even in the Note 7 incident, the Samsung incident, the incident rate was something like several hundred ppm. So that means several hundred per million. Mm-hmm. And that's a high incident rate in the industry, which is why it was a problem. But the average incident rate is only a few per million cells. Most of these, by the way, don't end catastrophically.
Right.
So, for example, to give you an example, Tesla designed their battery pack so that one cell can actually catastrophically fail without infecting the rest of the battery pack, right? So if let's say there was a manufacturing defect in one cell, and that cell would fail, and even that cell would overheat, the pack is designed so that does not cause the whole battery pack to go up in flames.
Right, so it can safely fail, essentially.
It can safely fail, exactly. The only real issues that we still see is if you were to get into a catastrophic incident where you damage a large fraction of the battery pack, mm-hmm. Then you would get all these runaway reactions in many cells. You would get electrolyte leaking out, and that would cause fire. An issue with lithium-ion batteries is that they contain an organic electrolyte, and the reason is this high energy density. If you again remember from your high school your high school classes, if you were to take water as an electrolyte, water you can decompose with a voltage, right? That's at about 1.2 to 1.5 volt. Mm-hmm. So you can never make a high voltage cell with aqueous electrolytes. If we could do that, that'd be great, right? Because water's safe, water can't burn. So in high voltage cells like lithium ion, we use organic solvents, mm-hmm. And these are very combustible, almost by definition. They are almost like gasoline. And so what happens is that if I were to puncture a hole in a lithium ion cell and the electrolyte leaks out, I have a sort of flammable substance. And in a big battery pack, I also have high voltage around. Like typical car packs can have 300 volt because they put cars in series. So, if I'm in an accident, there's probably sparking going on, and mm-hmm. I have this organic solvent leaking out, which is very combustible, and that sort of, bam, goes up in flames. But in the end, it's really not that different from gasoline, right? I mean, gasoline is a highly flammable substance, but hey, we sit on a tank with 20 gallons of it.
So batteries obviously have a lot of uses for us, but also, as we've discussed a little bit, there are still some problems with batteries. They can lose their charge after a time. If they're damaged too badly, they can heat up and explode or cause fires. So talk a little bit about what we're looking at for the future of batteries. What are some of the ideas and technologies and the up and coming versions of batteries that we might see coming into our devices in the future?
Yeah. So, fascinating question. So I think that, obviously we always want more energy, right? It seems like there's sort of an insatiable appetite for always more energy. So there's a lot of work being done on can you make these electrode materials store even more energy? And so both on the anode and the cathode side, there's interesting work. Today, the anode side is largely graphitic carbon. People are trying to replace that with silicon or even metallic lithium, which would allow you to hold much more charge in the same volume. On the cathode side, people are trying to come up with new, what they call intercalation oxides. So the way lithium is stored on the cathode is by literally shuttling into a crystal structure, almost like crystal structure, almost like sponges. They can take up lithium. And so we were trying to make new materials there to store more lithium. But maybe the most exciting new direction is to deal with the safety issue. So remember, I told you that this organic electrolyte is very combustible. So about 5-6 years ago, people discovered that there are actually solid-state electrolytes that conduct lithium really well. And so people now have the idea of making complete solid-state batteries, so where even the electrolyte is solid, mm-hmm. so there would be no combustible liquids anymore. And that's a very exciting idea, right? Because if there's no safety problem at all anymore, we would put batteries in many more places. We wouldn't need all the safety systems. That would save cost, save weight, volume. So that's an exciting new direction.
So there's definitely in modern electronics, and especially in the last 10 years, there's been this move to get things like phones, laptops, tablets, smaller and smaller and smaller. And we're at a point where it seems like the limiting factor in the size of a device is the battery that we use in it. A lot of these devices can't really get any smaller and still be expected to make it through the day with all the demands that we put on it from an energy perspective. So if we look at the lithium ion battery, which I think it's probably safe to say will be with us for at least a little bit longer, is there a lot more that it can be improved, both in the amount of energy it gives or in the efficiency we can get from it?
I think there isn't. First of all, it's a good observation. We now, our devices, I joke now that, if I look at my laptop, it's not really a computer, it's a battery carrier.
Yeah.
You're absolutely right. Making them smaller is actually counterproductive because you can't fit a large battery. And if you actually were to slice open, say, an Apple laptop, which I don't recommend you do, but you can look up it on YouTube. It's actually surprising. It largely contains batteries. People think it contains electronics. No, it contains largely battery. And there's a little bit of space for the electronics. It's indeed true that sort of becomes the controlling issue. Now, can we do better? There's actually still quite a bit of room left for improvement. As I mentioned before, people are working on higher energy density electrode materials. People are working on solid state. So I wouldn't be surprised that over time, there's still sort of a factor of 2 left in energy density improvement.
So a factor of 2 sounds pretty good, but I wonder, are there ideas or sort of pie in the sky theories for ways that would really reduce the size of our batteries?
Sadly, the answer is no.
Aww.
I know that people would like us to say yes, but there are really, I think energy storage is not one of these technologies where you should expect a factor of 20 improvement. It's not like microelectronics, right? With the people always ask, why is there no Moore's law for batteries? And the answer is very simple, right? In transistors, less is better. Mm-hmm. The smaller you make it, the better. Because the faster it can switch and the more you can pack together. In energy storage, it's actually the opposite because energy is stored on matter, right? You put electrons on atoms. And so you always need a certain amount of matter to store energy. And to a large extent, battery capacity scales with how much matter you have. So there's very little hope to sort of say get 10x improvement, just because of that sort of fundamental piece of physics limitation.
Reality gets in our way again.
Yes, sadly, reality gets in our way. There are sort of holy grails out there, right? They probably wouldn't really work for electronics, but maybe for larger scale storage that if you could do, if you could get energy out of liquid fuels and do that reversibly, right? So, fuels carry energy with them, right? Because when we combust them, they release that as heat. But you can also, in principle, do that electrochemically, right? And electrochemistry is what goes on in a battery. And there are some basic theorems that show that if you do it electrochemically, you can do it with much, much higher efficiency. Again, for comparison, the way we get the efficiency we now get out of fuels, let's say when you combust them in your car and then that, converts to mechanical energy to drive your car, is maybe about 25%. If we do that in a power plant, by the way, if we burn, say, natural gas in a super modern, optimized power plant, we can actually almost get to 50%. Now, there's actually a theorem that says that if you could do it electrochemically, you could actually get 100%.
Wow.
But that's a theorem, right? That doesn't mean we know how to do it.
Right.
And so to make a battery, we would have to be able to do it reversibly. Remember, we talked about this in the beginning. We would have to get the energy out and also put the energy back in. Mm-hmm. And, if you take a very simple chemical molecule like hydrogen today, right, you can make hydrogen react with oxygen and make water. And that's an electrochemically, you can get energy out. And we can kind of do that at, say, maybe, 70% efficiency, maybe 50% efficiency. But now we have to do it the opposite way again, right? Split the water. And water wouldn't be, and we can sort of do that again with sort of 70% efficiency. So round trip efficiency is below. And on more complicated fuels, we have no idea how to do this electrochemically. But if we could literally have a battery that would just use liquid fuels back and forth. And that would have super high energy density. That would have the highest energy density we can imagine. And that would be like 10x better than, say, lithium-ion batteries. But we just don't know the science of that. We don't know the technology of that. So it is a bit pie in the sky for now.
I love this idea. And when I start to think about or hear people talk about ideas for big kind of industrial size batteries, especially some of these really unique ideas, it kind of in my brain hits me right in the like steampunk area. It feels almost hacky, like we're trying to hack something, but a battery is really just something that stores energy. And we think about that as being chemical, but it can be potential energy as well. Like you say, it can be something that you roll up to the top of a hill.
Yeah, it can be anything. I mean, for a while, there were lots of effort in, can you just store energy by making something spin very fast? I mean, they were called flywheels. So, if you spin something, the energy stored actually goes up like the square of the rotation velocity. So it doesn't go up linear. So you can store enormous amounts of energy if you spin something really, really fast.
Huh.
And so people were designing these flywheels that literally would do 100,000 RPM.
Wow.
And when you run the math, you can store a very large amount of energy in that way. It sort of technically failed because the devil's always in the details, right? That you had to make things like bearings that could spin at 100,000 RPM and would be perfectly centered. Because, like, imagine that you have a wobble, right? You're spinning a flywheel at 100,000 RPM and it starts wobbling.
Uh-huh.
Now, this can release all its energy in like less than a second, right? Let's say that flywheel breaks. It would literally shoot pieces, through walls, through concrete walls and everything because it has so much energy.
Huh. Interesting ideas. You work in a fascinating field, sir.
Thank you.
If you'd like to learn more about Gerbrand Ceder or his work, we have links to get you started, which you can find on the show notes for this episode on our website, scienceforthepeople.ca. Up next, we speak with Dr. Kathryn Toghill, an electrochemist, about redox flow batteries and the problems of energy storage at industrial scale. Stay tuned.
Science for the People is a weekly radio show and podcast that explores everyday life from a scientific perspective. We are a member of the Skeptic Network, a collection of blogs, podcasts, and video content focusing on science and critical thinking. To find out where Science for the People airs near you, or to listen to past episodes, check out our website at scienceforthepeople.ca. You'll also find links to support us at Patreon, to connect with us on Facebook and Twitter, and to subscribe to the podcast in iTunes. And now, back to the show.
With me is Dr. Kathryn Toghill, an electrochemist and lecturer in the chemistry department at Lancaster University in the UK. Her research focuses on developing better electrochemical energy storage systems so we can better harness renewable energy from wind and solar power. Kathryn, welcome to Science for the People.
Hi, it's good to be here.
So you spend a lot of time thinking about redox flow batteries. So can you talk about what those are and how they work?
So a redox flow battery is a large-scale energy storage device. It's typically for the storage of renewable energy from wind and solar that is intermittent. So it's a way of translating the energy from an intermittent source onto a storage system that can give that energy back when you need it. And so it's therefore an energy storage system that's designed for long-term duration storage. So it's long duration delivery and storage, so it lasts more than 4 hours. So lithium-ion batteries are more familiar with people. That's more for your high-power applications and they're shorter term, whereas a redox flow battery system will operate for a long time because it has a massive capacity compared to a lithium-ion battery. So a way of describing them, the way I look to try and explain what a redox flow battery is, it's more like a hot water system, if you like. So it's a way of using that electricity to charge up a liquid electrolyte as you would with a filament in a heater to heat up some water. And you store that hot water until you need it later on. But unlike a hot water system, the tanks of hot water don't then dissipate in energy. They're separate from each other, and they store that electricity until you need it. So you just then reverse the polarity of your central stack, so that where that filament was, essentially, that was giving the electricity, you then put the electricity back into there and return what you put in. And they're very efficient systems, so they have about 90% round-trip efficiency for the ones that are state-of-the-art on the market right now. So that's typically the design. So you've got two tanks of electrolyte, which is where your charged species are. So everything's in solution, nothing's a solid material in a redox flow battery. And then you pump that liquid through a central stack, your battery, where your electrodes are involved, and you either charge or you discharge that species that are in the stack. And when they go through there, you get your energy in or you get your energy back. So it's a really simple system.
So where does the energy go exactly?
So you'll have a vanadium 3+. So in this discharged state, when the electrolytes, all the metal ions in solution, when they're not charged, but they are charged in a way, but when they're in their non-charged state, in terms of the battery, on one half of the cell, you have a vanadium 3 species. So that means it's charged to a 3+ state. And on the other half of the cell, you have a vanadium 4+ species. So it's charged to a 4+ state. And then when you charge it up, you can insert an electron into the vanadium 3+ species to make it a vanadium 2+. So that's made it more negative. And then equally, you have to do the same, an equal and opposite on the other side. So you take an electron from the other side to make it a vanadium 5+ state. So the vanadium 4 becomes a vanadium 5. And it'll stay in that charged state. So they're separate from each other. This vanadium 2 and this vanadium 5 are separate from each other in the system. But because of the way they're charged, they thermodynamically want to become their 3+ and 4+ state again. So that means that the energy it took to drive that reaction, so every time we put energy into something, we're going against what it wants to be doing. So we're thermodynamically driving it into that state. We're forcing it. So it's the same with the lithium-ion battery. When we charge it, we're forcing it into being a state it doesn't want to be in. We're taking the lithium out of a material where it wants to be. And then when we let it run through a system in a battery, when we connect it up to release that energy again, it just goes back to where it wants to be. So we do the same with the vanadium. We pump electrons into one side and we charge it down to a vanadium 2+ state, and we extract electrons from the other side in the counter reaction and make it into a vanadium 5+ state. Your vanadium 2 is a nice purple solution, your vanadium 5 is a nice yellow solution, so we can tell when it's fully charged. So while they're separate from each other, that energy can't go anywhere. As long as we don't put anything in those two solutions which can abstract that energy, then we are in a system that is just going to stay charged as long as we need it to be. And it's separate from the electrode and separate from anything else. So we can store that. They can be stored in tanks far away from each other. It doesn't really matter where they are in proxy, but they can be stored in large tanks, and we can put as much liquid in there as possible. They can have the vanadium 3 in with the vanadium 2 because that can't, on its own, that can't take the charge away. You need a full circuit to enable the discharge of the battery. So as long as those two things are separate, then we can keep all that energy in those liquid electrolytes for as long as we need. Does that make sense?
Yeah. So it sounds like is the way we change the states is the electron jumping from one solution to the other. Is that how that works?
And it goes from the electrode to the solution. So you've got two separate. So the two solutions, the two tanks that are circulating, they never interact. So you've got two separate solutions which don't interact at all. They are pumped through simultaneously, and they're separated by a membrane in the middle. Okay. And this membrane allows for protons to go between the two solutions. So it's an ion exchange membrane. In different chemistries, you'll have different ion exchange membranes because it'll be a different species in the solution that's maintaining electron neutrality. So the only way you can get a circuit to work, I don't know if you've made a battery cell before, or an electrochemical cell at all before, but you have your two electrodes. The bare minimum you need from an electrochemical cell is two electrodes, a solution that they're in, an electrical connection between the two electrodes, and then this still won't work until you have a salt bridge. Once you put a salt bridge between the two solutions, that's when you'll have a working circuit, because you can't move electrons from one side to the other until you have an equal and opposite positive charge moving through the system as well. So the membrane stops any vanadium in different charge states from crossing over from each side. So you can't have any vanadium-2 that's charged now going across to the other side and just discharging in the positive side. It's separated by that membrane. But you do get protons because this membrane is specific to protons, so it'll only allow the acid solution to go back and forth. So when the electrons move into the vanadium-2 when it's charging, you'll get protons moving from the positive side into the negative side as well to maintain to keep it neutral, because you can't just create energy. You can't generate, as we know from thermodynamics, we can't just put energy into this thing and not have an equal and opposite charge in there as well.
Right.
Do tell me if I'm explaining it too abstractly or
no. I think I follow.
There.
It seems like definitely one of the benefits of this is that you don't need to store your solutions anywhere near where this is actually taking place. It seems like you can sort of pipe it in when you need it, and you can just choose to not pipe it in if you just want to store that for a long time. Is that correct?
Yeah, that's exactly it. That's the particular advantage of a redox flow battery is that you're not. So what we look at it as is that your energy capacity, your storage capacity, is separate from your power capacity. So your power comes from the central section with the electrodes in it. So the amount of power you can get from a battery depends on how quickly that charge passes from the electrode to the solution. Whereas your storage capacity is how much liquid you have in a redox flow battery. So you could have literally tons of electrolyte, which is what you will have in a commercial redox flow battery. You'll have like 10,000 liters of electrolyte in one tank, but you might have a central stack which just has 20 cells in it, and that 20 cells will charge and discharge that entire volume of electrolyte. But it'll do it very slowly, and you won't get very much power out of that system. So what they'll do is they'll modulate how many, depending on the needs of the battery, you will modulate how many stacks you have. So you can have lots of stacks and a small volume of electrolyte, which means you'll get a lot of power, but you don't have much capacity to store energy. Or you can have a few stacks, but a large body of electrolyte, and that means you can store a lot of energy, but you're not going to get that energy back and forth very quickly. So it's not very good for high power installations. So when we need to deliver a lot of energy on the grid very quickly, one small redox flow battery is not going to be very useful because it doesn't have that power output capacity. But it does have. But if we need to trickle energy for a long time and we don't know when the lights are going to come back on to it or when the power is going to be reinstated, and we're going over 4 hours, typically that's when your redox flow battery is going to be very useful because it can deliver a steady amount of energy over a prolonged period.
This is quite interesting because it sounds like the modular structure of how this is engineered and how this works actually makes it really, really flexible depending on what your end needs are.
Exactly. Yeah, it's a very, very flexible system. It can be made grid scale. I mean, in China, they have just installed, they're in the process of installing like the biggest system. I think it's a 400 megawatt hour, system. So megawatt hour is our term for energy storage, and then power is just megawatts or kilowatts. So when we put the time constant in there, then we also have an energy scale. So just people confuse the two. So it's a common confusion to go from power to energy capacity. But a huge storage system is being installed in China at the moment, which is based on the vanadium technology. There are loads of installations coming up in the US, similar. So they typically get positioned because you're looking at, for one redox flow battery, it's a small container, a shipping container size, if you like. Probably smaller, but half a shipping container, I'd say.
Yeah, I would have estimated that would be bigger.
Yeah, but half a shipping container would be your vanadium footprint. So the one we had one installed because they stack on top of each other. So it's not even footprint, because then you can start going higher instead of having a bigger area. There's a 4 megawatt system in megawatt hour system in northern Germany that I visited, and that's got all the electrolyte is down the bottom, and then on top are all the stacks. So all the volume for the liquid electrolyte is down the bottom half of this stacked storage container. And Yeah, it's no bigger than something like 4 meters by 8 meters or something like that. Not 8 meters, that's too big. 4 meters by 2 meters by. I've installed one. I'm trying to remember what the specs are, but they're not very big. And you can put them next to each other, and then you can, if you want, you can just put lots of these modular systems next to each other, and then you can you can connect them all up as well individually. So as your capacity grows or as your needs grow, you can then add more and more systems. And they can go anywhere, which is another advantage of redox flow batteries, is that they're not geographically limited.
Right.
Like a lot of energy storage systems are geographically limited. They're also suitable for a black start, so they're not something that depends on having energy, because they'll have a residual amount of energy in them anyway.
Right.
You never discharge them to the point where they've got no energy left in them. They have a capability of being started when there's no energy available at all. So, because a lot of the things like compressed air storage and things like that depend on having energy to start it up. So if you have a complete blackout, you can't access that energy storage, that stored energy, because you need energy to start it. Whereas batteries typically have energy in them already, so you can start them without having other things, without needing grid to kick it off.
So it can kind of start itself.
Yeah, that goes for all batteries typically, but yeah.
You mentioned that redox flow batteries were quite efficient. So what type of efficiency are we getting compared to other types of batteries that people might know more about, like a lithium-ion battery? Yeah,
they're about one of the highest in their efficiency in the flow battery, because there are fewer processes to consider in the actual in the charging and discharging. It's what we would call an outer sphere reaction with the electrode. So it's just the charge and discharge at the electrode surface from the liquid. There's no need to intercalate any solid material. There's no development of any solid material at the electric surface and dendritic growth. You're not trying to prevent anything like that you would in a lithium-ion battery. So the charge and discharge profile can be varied a lot easier than it can be in a lithium-ion battery. Lithium-ion batteries are really efficient, but it depends how you're using them.
Right.
They're less efficient the harder you drive them.
Right. I remember hearing from a previous interview, actually, where things like the lithium-ion batteries in our phones have been engineered in particular to be able to charge up faster, but we sacrifice kind of their longevity that way. They won't last us as long because we want to be able to power them faster and recharge them faster.
Precisely. And they're brilliant for power, like for doing portable technology. So that's where your lithium-ion batteries come in, and your other energy devices, nickel, cadmium as well. So there's different renewable electrochemical storage systems there that are perfect for that short-term duration. And then you've got your long-term duration, which is 4 hours plus typically. Now, redox flow batteries work there's a grey area. These don't just cut off like a redox flow battery works at 2 hours and it works at 1 hour as well, but it becomes more cost-effective to use it at 4 hours plus and have it as that application specifically. Lithium-ion batteries are more cost-effective as short-term duration batteries and not entering that 4 hour plus area.
Okay.
So people are trying to employ lithium batteries to do long-term storage now, but it's really not a cost-effective approach when there are other technologies that are more cost-effective in that category. So, your stationary storage, if you like, your lithium-ion, your redox flow batteries, and then other systems such as, the sodium sulfur high temperature battery is huge. It's a huge battery that uses ceramic. It uses molten sodium. Horrible chemistry inside. Really, don't ever open one up. But you wouldn't, because they're on scale. Nasty sodium batteries with a ceramic solid membrane between them. That's how they work. They've got a special one that transports sodium to and from a polysulfide side. So then you've got horrible sodium polysulfide compounds, and you've got molten sodium. So if you ever open that up to air, you're going to have a bit of a fire. But nonetheless, they're incredibly powerful systems that have a lot of energy in them.
I think I read an article where someone was trying to use carbon dioxide in redox flow batteries, which would potentially be great for reducing kind of impact on climate change as well, because you can sort of start to look at recycling some of the carbon dioxide pollution that's created. But I don't know. I just sort of remember reading that somewhere, and I have no idea if that's accurate.
You didn't read that in my stuff, did you?
I don't think so, no.
It's just because I did carbon dioxide utilization as well. So that's the other bit of research I do. So I do redox flow batteries as one area, that's the chemistry of that, and then I'm looking at carbon dioxide conversion to synthetic fuels.
Oh, interesting.
And
so
I have an idea of splicing the two together, but yeah, I haven't really.
Synthetic fuels to replace things like petrol.
Yeah, because we can't do without petrol and things. There are some applications that batteries just not going to cut it. Mm-hmm. Like flying, for example. Are you wanting to fly across the world in a battery powered plane, or you want a tank of some kind of fuel just in case? I don't know if batteries is such a high power demanding process, flying. I don't see how you could use a battery to achieve it.
Right. We might be able to use batteries to offset the amount of fuel we need, but we're going to continue to need fuel at least for the foreseeable future in things like planes, anything that's
a long distance travel as well. Long distance traveling of things. It takes a long time to charge a car battery. Unless we shift to hydrogen fuel economy for travel purposes, because you can refill a hydrogen fuel cell car really quickly. Mm-hmm. Hydrogen just comes in like it would petrol. But the storage of hydrogen is difficult. But that's been developed. But we don't have hydrogen fueling stations across the country, so that's limiting the investment there, because the infrastructural change is huge. With electric powered cars, I would love an electric car, but there's nowhere for me to fuel it. There's nowhere for me to charge it in my street where I live. So, and I don't see how they could feasibly install that in the street, because I live on a terraced street, so there's all the houses stuck together, and I'm in the middle, and there's no specific parking. You can just park on the street anywhere. So, I mean, that's how most of the UK operates in living space. So I don't see how you could charge at home.
That is definitely one of the biggest problems I think we're going to face with the adoption of electric cars, is just where do we charge them in the infrastructure that's required, and the changes that would need to be made. People think about things like making sure you can charge your car battery in your house if you've got a garage. But like you say, a lot of people who live in denser areas, like where I live in the UK, like where you live in the UK, you park on the street. And so what's the solution there? Is it every, car length, there's somewhere to charge a car? That adds a lot of infrastructure baggage onto creating a street.
As well.
Yeah. And
it's just because generally there's I know there's charging stations on my campus, and they're really trying to push us to get electric cars here on campus. But I'm like, okay, I could get one, but what if I need to drive 100 miles north to do something, like the Lake District's north, and then or if I need to travel somewhere a bit more remote to go to a conference or something like that, then I don't know what car. I wouldn't be able to use my electric car, because I wouldn't guarantee there would be a charging station there or on the way, or you kind of want your backup fuel-based car, just so that you know that you can just pump some fuel in there and you can be somewhere, and you can even take some fuel with you if you were unsure if you're going to have fuel at the end.
And
it's just a bit.
Even if you knew there was a charging station on the way, if you have to sit and wait there for an hour or 2 hours.
4 hours. It's 4 hours to charge an electric car. So these are when you said about CO2, so this is where I'm looking. I like stationary storage in batteries, and I'm looking at CO2 reduction to fuels and trying to repurpose that and make synthetic fuels, because I can't see a world where we don't have it. But it should make it a circular process. Like, you should get carbon neutral synthetic fuels, if you like, because if we repurpose, if we try and capture CO2, which there's a lot of that going on, and then we can reuse it then, and we can use renewable energy to drive electrochemical reactions to reduce that into a synthetic fuel. I mean, there's lots of research going on in this area. It's just a very challenging reaction to achieve and get something, a product of high value, because we can very easily get carbon monoxide and we can get formic acid, but neither of them have. Well, carbon monoxide definitely doesn't have much energy, and the formic acid won't give you very much back. So when we want to go back to methane, or we want to go to alcohols or something like that, because we could use them as a fuel, that's a more challenging reaction. But it's another area. I mean, because energy storage doesn't stop at batteries. Energy storage is any way of capturing energy from one source and putting it in something else where we can reuse it later. So that's also power to gas and doing electrolysis of water and generating a lot of hydrogen. That's carbon neutral. Because the hydrogen we buy and use is actually from a carbon shift reaction.
Okay.
And generates a lot of CO2.
Oh, wow. Okay.
It's so the most part when you get hydrogen, for fuel cell cars and things like that, you got to wonder where the hydrogen's coming from, because you need to have an on-site electrolyzer that will convert water from electricity. So using electricity to split water into hydrogen and oxygen to make your hydrogen and ensure that that's where it's come from with high purity to go into your fuel cell system and to go in your hydrogen fuel network, and not have it coming from the far quicker process of doing the carbon shift reaction and generating more CO2, because then you've just made a non-carbon neutral system.
Right. We sort of, as a human race, worked our way into a bit of a tough corner, because we've built so much infrastructure around the non-renewables, and the non-renewables work really well. You know, we've been able to get really far with them. And so anything we want to try and replace non-renewables with needs to be able to fulfill the same requirements, right? It has to be a replacement. If we lose functionality, let's call it, with the replacement, then it's very difficult to make that replacement catch on at all, if it means you have to sacrifice or, there's obviously going to need to be infrastructure changes no matter what. But
there needs to be huge changes, yeah.
Yeah, it's very hard to move away. It's such a multi-pronged problem.
It's one of the things when I teach on this subject, I start with, right, so there's what you have to know when you're developing new technology is that whatever happens, the society expects electricity to be on demand.
Yes.
And it expects it to be in a refined form. So it expects to have energy on demand and expects it to be in a refined form. So that's the expectation of society. And you will not have a society agree to having a step back in that. So you can't go backwards in your development. You have to always go forwards. You can't say, look, this is actually a far more environmentally friendly method if we do this, but it does mean you can have a little less power for a bit, and we're going to have to be a bit more careful with how we use our energy for a while, just while we reset. You're never going to get a consensus on that.
No, because
people do not accept.
At the end of the day, I still want to plug my phone in and be able to use it all day.
Because as much as we have a nice open mind going, and you'll have some people who are going off grid and wanting to do their bit, but for the most part, and this is how we continue, and it's the same in my department, while I'm developing new energy systems, I need a lot of energy to do it. You won't get society as a whole agreeing to stepping back on their energy consumption. They'll only ever continue. So all we can do is develop ways to make it more efficient and make it green from the outset. We can't step back on it. So that means we have to find ways of replacing our energy without compromising it.
It seems like it would be even more difficult from the standpoint of researching new methods when we're also at the same time making the old methods based on non-renewables oftentimes more efficient or more able to keep up. Like lithium-ion batteries do keep getting better. So that means that any replacement that we hypothetically might create someday also needs to keep up with the development of the stuff it needs to replace, it's a tall order.
We create reasons to use energy. I've seen a photograph. Somebody was talking about this before, and they had a photograph of a iron, like a clothes iron, which was one that you heat on the fire, but it had a plug that had been retrofitted to it, and it was like they made a system that didn't need electricity. So a lot of electricity demands have come because they created technologies that no one had before, but that need electricity, but no one had electricity. So they made a technology that demanded electricity, such that people then wanted that system and then needed electricity. So they create a technology that shifts the demand of the household or whatever. So television is a particular example of that. So people didn't have television. Then when they had television, and more people want television, which meant more electricity was necessary. And so it's where technology makes a demand in storage. So when we didn't have mobile phones, we didn't need as much energy. Now we've got more and more mobile systems, and yes, they are lithium-ion based, which makes you think, oh, well, I'm not making lots of CO2, but the generation of electricity to power that and charge that system is coming from fossil fuel power plants and things.
Yeah, and especially when you consider that every home probably has 3 or 4 phones in it that now need to be charged.
Yeah, and how many houses have cars have multiple households as well? Because cars have been made cheaper and more efficient, and they go, well, we've made things more efficient. So people, when things are more efficient, they think they can have more. The same when you tell somebody that the cake has 30% less fat, they'll have 60% more. So they think they're offsetting, but they actually have more than they would have anyway if they'd not known that. So people think. The psychology of energy use and energy demand is a very interesting area, and that's also influencing how we use, because energy needs are going up. So what's brilliant is, was it last year, April, was the first time that despite energy consumption going up, globally our CO2 levels didn't rise. They stayed the same.
Oh, okay.
And the reason they've speculated as to why that happened. Now, there is definitely climate change, and I'm not climate change, and there is definitely a need to reduce our CO2 levels and things, but it was the first time CO2 didn't go up as well. And it might have been 1 year normally, I don't know. But they attributed it to the penetration of renewables. We're starting
to get enough of them in that it's starting to make a bit of a difference.
That it's carbon neutralizing us. So did that 1 year, I think it was 2014. And it was an exciting time because I was like, wow, that was an amazing stat I read. Because in the UK, I mean, the solar energy penetration is massive now. It's huge. The amount is going in at the rate it's going in, because suddenly they made a manufacturing process that brought that cost right down. Mm-hmm. And then solar became far more accessible. And as that's more accessible, that's driving the need for energy storage. Because 10, 15 years ago, people were developing energy storage devices for stationary storage, but the governments weren't interested and nobody was investing because there was no demand for it.
Right.
Because we didn't have the renewable. We didn't have the intermittent storage. So instead of looking forward and thinking, well, we're probably going to introduce this later on, so maybe we should develop this technology now, it's not been the case. Everything's happening retrospectively. The surge in energy storage is only happening because in response to the surge in renewable penetration.
Right, so we've essentially created...
We're not ready for it.
We've essentially created...
a demand for it.
Right, we're starting to create a demand for it, and so we're answering that demand by starting to create
But we're always
solutions.
catching up, yeah. Exactly, so it's frustrating.
Well, Kathryn, thank you so much. Really interesting topic. Every time I read about batteries, I go down a battery rabbit hole. Because there always seems to be...
As I've just talked for way longer than I was meant to, you can see I do as well.
It's just there's so many interesting ideas and a lot of new interesting chemistry in the design of new batteries. And I think as well, like, I often forget that there are still new things happening in chemistry. Chemistry sometimes feels like that science that we don't hear very much about, that sort of all the things have been discovered, and so there's nothing really new in chemistry. But that's really not true, and I think batteries is one of those ways into some of the new stuff and new ideas that are happening in chemistry.
Oh, certainly. So much to do. So little time.
I'm sure it will keep you very busy.
Yes.
If you want to learn more about Dr. Kathryn Toghill, her work, or redox flow batteries in general, we have some links to get you started in the show notes for this episode, which you can find as per usual on our website, scienceforthepeople.ca. If you often find yourself on Facebook or Twitter, you can also find us there too. We happily accept any follows, likes, retweets, or shares you might want to give us. If you've got a few spare minutes, it would be great if you could rate and review us on iTunes. It helps more people find us, and if you've enjoyed this episode or others, probably someone else will too. And finally, if you'd like to support Science for the People, please do consider becoming a Patreon supporter and throwing us a couple of dollars a month so we can keep the lights on. Maybe you've noticed there weren't any ads on this episode, or any of our other episodes. That's because we are a volunteer-run show, supported by the kindness of our listeners and their donations. Those donations help us keep the lights on and the episodes coming. So if you have $1 to spare every month, do send it our way via our Patreon. Thanks for listening, and we'll see you next week on Science for the People. Science for the People is produced by Rochelle Saunders and edited by Ryan Bromsgrove. Helen Quivalon is our publishing liaison. We get research help from Josh Witten and consulting support from Desiree Schell. Our frequently seen guest hosts are Marion Kilgour, Anika Hazra, and Jessica Yaros. Our theme song is called Binary Consequence, and it was written and recorded by Fractal Pattern. Science for the People is entirely listener-supported. You can find us on Patreon, where you can support us with monthly donations in any amount, or you can send us a one-time donation in any amount via the donate page of our website. Science for the People is created in partnership with the Skepchick Network, a collection of blogs, podcasts, and video content focusing on the intersection of science, popular culture, politics, and social justice. You can find out more about Skepchick at skepchick.org. The show is hosted by science news writer Bethany Brookshire and me, Rochelle Saunders.